Anyway, let's prove this weak law of large numbers. Okay, here's the proof. First of all, we have expectation of Sn is equal to the sum of expectation values, right? And that is n mu, because the expectation value of all of these are mu, right? So that means if you divide both sides by n, we have expectation value of Sn over n is mu. Yeah, we've seen this before. Okay, so the expectation value of the square deviation of this quantity from mu is actually the variance of Sn over n, right? Now, from the property of variance, Sn over n, so n can go out, and when it goes out, it becomes squared. And variance of Sn, okay. Oh, I think I forgot one important conditions. They are all independent. Okay, x1, x2, and so on. They are all independent. Since they are independent, remember this S is the sum of independent random variables. So since they are independent, this variance can be split into the sum of variances. Okay, but we have imposed one condition here. These variances are less than or equal to some constant, which is finite. So this summation is less than or equal to this constant. Okay, but this is a constant, so we have n squared and nk, and n can cancel out, so we have k over n, which converges to 0 when n goes to infinity. Okay, so that means this converges to 0, and the proof is done. Okay, so this was the weak version of the law of large numbers. So there should be the stronger version, right? So of course there is a strong law of large numbers, but the proof of that is a little bit difficult, but I will still explain what that is. Okay, uh, let's say again we have random variables, a sequence of random variables, and they are independent, and we have the expectation value of them equal to some constant mu, and also we impose this condition: expectation value of xi to the power of 4. That means the fourth moment about 0 is bounded. Okay, actually there are many versions of uh, strong law of large numbers depending on the conditions we impose, but here we impose this condition. Okay, And if we define Sn as the sum of these, not infinity, it's n random variables, then we have this result. Sn n equal to mu is 1. Okay. And here we say, if this is the case, this is the probability that this limit converges to this constant is 1. Okay. So in this case, we say Sn over n converges to mu almost surely. Okay, almost surely. So this is a technical word. So this sounds quite ambiguous, almost surely, but actually this has a clear meaning. It means the probability of this is 1. Okay. So what's the difference between the weak law and the strong law of large numbers? Let's compare those. Okay. In the weak law, we said the expectation value of this deviation is converges to 0. Okay. And strong law, we say the probability that this converges to mu is 1. Okay. So what we notice here is the limit is outside expectation here in the weak version. And in the strong version, limit is inside this probability. Okay. Remember, this Sn is a random variable. Okay. So this whole statement here inside this parenthesis is actually a subset of omega, right? So this really means subset of omega such that limit of Sn of omega over n is mu. Okay. So if this is equal, the probability of this subset is equal to 1, that means, roughly speaking, this subset is actually almost the entire omega. Okay. Remember, the probability of omega itself is 1 by definition. So if the probability of this subset, this event, is 1, that means it is almost all of omega. Okay. So that's what the strong law means. On the other hand, this one, okay, this is the limit of expectation value. As expectation value is already a number, right? So inside this is random variable, but we already integrated this square deviation. So expectation value itself is a number already. So we have actually a sequence of numbers, and that limit converges to 0. Okay. So that's the difference in the meaning. And why is this strong and why is this weak? Why? Well, uh, that is because uh, this strong law is more stringent. I mean, strong. If this holds, then the weak law holds, but not vice versa. Okay. If this holds, sometimes this may not hold. Okay. So even if the variance of the sample mean converges to zero, it does not mean that the sample mean itself converges to the mu. Yeah, so this is more fine condition than this one. Okay. Maybe I should explain a little bit more. So variance of 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 sample mean converges to zero means like this. So if you increase n, the spread of lots of sample means will converges to zero. Okay, so it will converge to some value mean. So this variance converges to zero. But remember, every time you make a set of measurement, the sample mean has different values. Okay, so if you are unlucky, although the variance is a variance means average square deviation. Although the variance is very small, there may be some outliers here which do not coincide with the true value of the expectation value. This is possible with non-negligible probability. But in the case of strong law of the large numbers, that doesn't happen. Okay? Every time you make the measurement, it is almost surely very close to the true value. So that's stronger law. Okay? But the proof of this is a little bit involved and requires a lot of preparation, so we skip it. If you're interested, please study that in the future. Okay, that's all.